Hi dear students, welcome to Geeta's classes. In this class, we are going to see the Laplace transform of the function t power n into f of t. In the previous classes, we have seen Laplace transform of different functions and we have done problems using those functions also. So here the theorem says that if the function L of Laplace transform of a function f of t is f bar of s, then Laplace transform of t power n into f of t is minus 1 power n into d power n by ds power n of f bar of s. Please remember f bar of s is Laplace transform of f of t. Okay. So now we are going to prove this theorem. Here n can take the values 1, 2, 3 etc. So here we are going to use this theorem by using mathematical induction. What is mathematical induction? It says that you can prove, you have three steps in that. One is basis step, basis of the induction, and the second one is induction hypothesis, and the third one is inductive step. Okay, so in the basis step, we are going to prove that the result is true for n is equal to 1. And we will assume that result is true for n is equal to k, and you have to prove the result for n is equal to k plus 1. Okay, so we will prove this n plus 1, n is equal to 1 and n is equal to k plus 1. Assume that the result is true for n is equal to k. Then if you can prove like this, then by mathematical induction we can conclude that the result is true for all the values of n, all the positive integers of n. Okay. So first is basis of induction. So we have to prove the result for n is equal to 1. Okay. That is to prove that L of t power 1 into f of t is equal to minus 1 power 1. So minus of d by ds of f bar of s. Okay. So consider, what do you know by this definition? L of f of t is integral 0 to infinity e power minus st into f of t dt is equal to f bar of s. Okay. This is by definition, right? Instead of consider, you can write by definition. We know this. So now we have to differentiate both the sides. Differentiating with respect to s. Both the sides. We get, or differentiating 1. You can assign this equation as 1. So d by ds of integral 0 to infinity e power minus st into f of t dt is equal to d by ds of f bar of s. Okay. So now we have to take this d by ds inside the integral, that is by, we have Leibniz rule. By Leibniz rule for differentiation. Leibniz rule for differentiation under integral sign. We get integrals, when you are taking like this, integral 0 to infinity, dou by d by ds will become dou by dou s of e power minus st, because this is with respect to t, integration is with respect to t, differentiation is with respect to s. Okay. So t is independent of s, so you can write like this. This is d by ds of f bar of s. So this dou by dou s is applicable for e power minus st. That is, when you differentiate, what will you get? Integral 0 to infinity dou by dou s of e power minus st. That is differentiating e power minus st partially with respect to s. So this is minus t into f of t. Differentiating with respect to s. Okay. So what is coefficient? You have minus t with that, into dt is equal to d by ds of f bar of s. That is integral 0 to infinity e power minus st. This minus I can take it outside and I am going to write it in the right hand side. So t into f of t dt is equal to minus d by ds of f bar of s. Okay, this minus I am taking it this side. And if you have, what is this by definition? If you have e power minus st into f of t dt, we write it as L of f of t, L of f of t. So here you have, in the place of f of t, we have L of t into f of t. Therefore, this is L of t into f of t is equal to minus d by ds of f bar of s. That is, the result is true for n is equal to 1. Okay. Now let us assume the result is true for induction hypothesis. Let the result be true for n is equal to k. Let the theorem be true for n is equal to k. K means what? That is L of t per k into f of t is equal to minus 1 per k into d per k by ds per k of f bar of s. This is what we have assumed. Now, inductive step means you have to prove for n is equal to k plus 1. To prove the theorem for n is equal to k plus 1. That is, if you are taking k value, the next value you have to prove. So, n is equal to k plus 1. That is to prove that L of t per k plus 1 into f of t is equal to minus 1 per k plus 1 into d per k plus 1 by ds per k plus 1 into f bar of s. Okay, this is what we are going to prove. Now, what do you know? Given that by induction hypothesis, we know this result, right? L of t per k into f of t is equal to. So let us write the definition. So we know that, or we have, by hypothesis we have integral 0 to infinity e power minus st into t per k into f of t dt is equal to minus 1 per k into d per k by ds per k of f bar of s. This we know. So now again differentiating with respect to s, both sides. So d by ds of integral 0 to infinity e power minus st into t per k f of t dt is equal to minus 1 per k d per k by ds per k into f bar of s. That is, now again by Leibniz rule, you take this inside. Take the differentiation under integral sign. So this will become integral 0 to infinity dou by dou s of e power minus st into t per k f of t dt is equal to minus 1 per k d per k by ds per k f bar of s. Okay. So now you differentiate this. That is integral 0 to infinity e power minus st into differentiating with respect to partially with respect to s. So the coefficient is minus t into, already we have t per k into f of t dt. Already we have t per k into f of t. So I am writing it again. This is equal to minus 1 per k into d per k by ds per k into f bar of s. That is, now I am going to combine this, that is integral 0 to infinity e power minus st t per k plus 1 into f of t I am going to combine into dt, and minus I am bringing it this side. Already we have minus 1 per k, so this will become minus 1 per k plus 1. Sorry, here again d by ds, right hand side one more d by ds you have to write. D by ds of, sorry. So this will become d by ds, if I take it inside, this will become k plus 1. Okay. So here d per k plus 1, ds per k plus 1. D per k plus 1 by ds per k plus 1 into f bar of s. So what is this? L of t power k plus 1 into f of t is equal to minus 1 power k plus 1 into d power k plus 1 by ds power k plus 1 of f bar of s. Okay. So the result is true for k, n is equal to k plus 1. N is equal to k plus 1. So we have proved that for n is equal to 1, we have proved that it is true. And by assuming n is equal to k plus 1 is also true. Therefore, by mathematical induction, the theorem is true. The theorem is true for all positive integers, for all n, or all positive integers n. Okay, this is the proof. And all the proofs are important. Laplace transform of all these functions, anything can be asked in the examination. So please follow that. And previous classes, all the other proofs are available. Laplace transform of other functions. This is class 10. So up to class 9, I have proved all the other proofs. Please go through that. And please share with your friends and give a like if you like this class. Please give a thumbs up and share it with your friends so that it will be useful for them also. Thank you so much for listening.